Well, good afternoon or good morning, depending on the location in the world. My name is Petar Bukovcic, and I'm a research scientist at the University of Oklahoma Cooperative Institute for Mesoscale Meteorological Studies, and I'm an affiliate with NSSL, or National Serious Storms Laboratory. Today's talk is about the polarimetric radar QPE in aggregated snow. So I'll start with the table showing a multitude of ZOS relations listed in the literature and used by the WSR-ADAD community in the different parts of the United States. So the variability of the multiplier in this power law relations is an order of magnitude, as you can see from this red highlighted multipliers here. And it is not clear which relation should be used in any particular situation. This is why that little progress has been achieved for the radar snow measurements after the introduction of weather radars. So the primary reason for poor performance is similar to rain measurements if only the reflectivity factor is used. It's a variability of size distribution. But this is further aggravated by the variability in snow habits and in snow density if you're talking about the snow measurements. So in rain, reflectivity is proportional to the sixth moment of the particle size distribution, whereas the rainfall rate is roughly 3.67th moment. But in the case of snow, snow density, which is generally inversely proportional to the diameter, because of the snow density, which is inversely proportional to the diameter, reflectivity is proportional to the fourth moment of the particle size distribution, whereas ice water content is essentially the second moment, and snowfall rate is actually slightly higher than the second moment because of this snowfall velocity dependence of the diameter, this factor gamma here. So, excuse me. It can be shown here that the intercept of the exponential size distribution, NOTS, can actually change 4 orders of magnitude. And that is the reason why the multiplier of these SOZ relations are changing actually an order of magnitude. Our major hope for polarimetric snow quantification is KDP, which is roughly proportional to the first moment of the particle size distribution. And this is closer to the second PSD moment, which essentially this precipitation or snowfall rate is close, as opposed to the reflectivity, which is the fourth PSD moment. Well, on the negative side, KDP is affected by the shape and orientation of higher meteors, where Z is not. So this shape factor from this relation for KDP is actually dependent on the aspect ratio, and the orientation factor FO is dependent on the width of the canting angle distribution sigma. There are several polarimetric relations for ice water content or snowfall rate that have been developed recently. And some of them use only KDP or KDP alone. Some of them, as from Bukovcic et al. 2020, use KDP and Z, and as in Ryshkov et al. 2018 or 1998 to 2019, these use ZDR and KDP. So the KDP relation, where the KDP alone is used, is most prone to this dependency on orientation and shape because of the exponent of this relation. Whereas in Bukovcic relations, where you use KDP and Z, where you have smaller exponent with these factors. In addition, because of this KDP and Z, they're first and fourth moment, and if you use them, their combination is actually closer to the second moment, which we want to actually be close to, because of ice water content is almost the second moment, and snowfall rate is a little bit higher than the second moment. The KDP-ZDR relation actually has the lowest amount of vulnerability to this orientation and shape, and even in a size distribution variability, because the KDP and this factor 1 minus ZDR to the minus first are similarly affected by this, and because of the ratio, this dependency almost canceled. But the problem is with this relation that it is susceptible to these errors in KDP and ZDR measurements, and especially in ZDR miscalibration. The recent air mode measurements with X-band dual-pole radar and in situ measurements on board of Canadian aircraft demonstrate, as in the Goyen studies in 2017 and 19, that this latter relation actually is the most accurate for estimation of ice water content inside the ice clouds. Similarly to this, the snowfall relations are slightly different, but similarly effective as the ice water content relation. Well, in our study here, we used several of the standard S2Z relations here, as we will show a little bit later. And this relation of SOKDPZ and SOKDPZDR from Bukovcic et al. But there is a caveat here. If you want to use the KDP, it is low and noisy at S-band. So therefore, the additional spatial averaging is required to obtain a robust estimate of KDP and ZDR and Z as well. So recently introduced radar products such as quasi-vertical profiles or QPE, range-defined vertical profiles, quasi-vertical profiles or RDQPEs and column vertical profiles, they all imply this aggressive spatial or azimuthal averaging and represent radar data in height versus time format. The difference between these techniques is that QPE and RDQPE, these are radar-centric, whereas CVP is not, and it can be moved within the radar domain. In short, QPE uses the highest tilts and does this azimuthal averaging in full 360 degree, and then actually projects these values along the radial at this vertical, and that's why it's a quasi-vertical profile, and then forwards this in time, the measurements. Range-defined QPE is similarly constructed as a QPE, but it uses all available elevations, and then these are weighted to get the estimate in the vertical, and very useful, obviously, because you can go lower and closer to the ground with these kind of processing. CVP, similarly to this, is actually constructed if you predetermine to use the, let's say, box of 20 degrees by 20 kilometers, and then use the average of this and move it radially and in some prescribed distance, and then map it from all available elevations. We use extensively all of these in our studies, as you will see in next several slides. Now it's time to switch gears towards the results section of this study, and first of the cases that I'll present is nor'easter, or so-called nor'easter or East Coast blizzards. So from January 23rd, 2016, this is 1.45 degrees PPI from KLWX from Sterling, Virginia radar. So we see from this PPIs that this storm had a lot of these snow bands, as the enhancements in Z are very visible here. Then there are also enhancements in KDP, but I can tell you that the highest enhancement in KDP usually does not collocate with the highest enhancement in Z, because of course in aggregated snow and a higher degree of aggregation, KDP is low as well as ZDR, and the highest values of KDPs are probably around 0.2, 0.25. So some enhancements in ZDR are also obvious, and you can see from this image that ZDR is usually negatively correlated with reflectivity in snow, and some reduction in ρHV is actually coinciding with the highest values of ZDR, marking the pristine crystals or crystals, or some excuse me, some low concentration, or sometimes even high, depending on what the process is underlying or the snow habit. So you have to be careful with interpretation of these and have to know this beforehand sometimes. So next I'll show the snowfall rate and accumulations from this box, which is actually located above the ASOS ground-based station, and this is about 10 by 10 kilometers used for averaging, because as we mentioned earlier, you have to use really high degree of spatial averaging for these variables to be more accurate. The SOKDPZ relation is red, SOKDPZDR is green, and SOZ, standard SOZ relation is in blue here, and the gauge is the broken black line. So we see that SOKDPZ is most consistent with this peaks in S, but sometimes there are some overestimation or some inconsistencies, like in these several periods here at 3 UTC, maybe 6:30, maybe around 20. But overall, the comparison is very good, as well as for SOKDP-ZDR relation, which it's not far behind. The SOZ relation, in contrast, doesn't exceed 3.1 millimeter per hour during the entire storm. As you can see from the right-hand side panel, which is the accumulation, the most consistent line with gauge measurements is from SOKDPZ, and SOKDP-ZDR is not that far away, where SOZ is moderately underestimating the amount. Next, I'll show the evolution of these storms using the range-defined quasi-vertical profiles, which can be really useful if you want to look into the microphysical processes and even snow habits. So we see here that there are several snow bands passed over the radar site. These are radar-centric products. And the highest enhancements here in Z is during the high cloud tops, as well as for KDP. KDP is usually elevated in the dendritic growth layer, but sometimes there are these excursions below the dendritic growth layer, as I said, depending on the habit and the process that is going on. Perhaps the most striking signature is from ZDR, which here aligns with -15 degree isotherm, which is in the middle of the dendritic growth layer, which probably shows that pristine dendrites are formed here. The lower right-hand side panel shows the profiles of accumulation by using these variables from Z, KDP, and ZDR in this polarimetric approach, and from SOZ standard approach. So maybe the most prominent feature here is that this profile should be constant from, let's say, below the dendritic growth layer towards the ground if the mass flux is conserved. So SOKDPZ does pretty good job in this, and it's very close to this ground measurement through the whole depth of this layer from, let's say, 2 kilometers, 2.5. SOKDP-ZDR does pretty good job within the dendritic growth layer, or a little bit below the dendritic growth layer. And this is expected because you expect this relation to work the best from -10 to -20 degrees Celsius. And the profile of SOZ is the most unrealistic, even though the value of this SOZ profile at the ground is close to the ground measurement, but still it should be more constant with the altitudes until we hit the dendritic growth layer. Next case is from Oklahoma, and now we are using the CVP. As I said earlier, CVP is not radar-centric product, so if your point of interest is not collocated with the radar, this is a very useful tool for evaluation of these processes and even for quantification. So there are two regimes for this particular storm, and we are looking at this CVP above the Kessler's Farm, which is the OU test site, about 30 kilometers south from this our Caribbean radar. This from 2011 February 1st storm. So the first regime is from 8 to 14 UTC, let's say, and it shows higher cloud tops and heavier snow on the ground. And then later, two shallower cells passed over our site, Kessler's Farm. So again, there are enhancements of KDP in the dendritic growth layer around -15, and in this case, we see that there are excursions even down below all the way to the ground. And similarly to previous case, there are enhancements in ZDR. In this case, you can see them at the cloud tops as well, where the pristine crystals are, and then in the dendritic growth layer. But perhaps the most striking is this part of the storm later when we have these two cells, when we see that really enhanced values of ZDR, which is actually probably pristine dendrites or planar-like crystals with low concentration and which do not aggregate. And you can see here that there is an inverse correlation with ZDR and Z in aggregate itself. Lower right-hand side panel shows, similarly to previous slide, accumulations from these profiles. Here, see that polarimetric estimates as of S of KDPZ and S of KDPZDR with the red and a green line are almost constant from below the dendritic growth layer to the ground, which is what ultimately, we expect. And S of KDPZDR shows a little bit more consistency with this and very good result with ground measurement. S of KDPZ is that far behind, where S of Z again shows a little more inconsistent profile, and only from this ground level to maybe 1.5 kilometers, there is some constant values here. The next case is actually a orographic case from Colorado. This PPI shows that there is a snow band here caused by orographic lifting, and the enhancements of Z and KDP are almost collocated. ZDR is usually higher at the storm edges in this particular setting, where OHV is almost uniform. This case is actually it's not uniform, so we had to use a smaller area for averaging, and it's about 5 by 5 kilometers. And because of this, the accuracy of the polarimetric variables is not as high as if you use it in a range-defined quasi-vertical profiles or even for CVPs. But the instantaneous snowfall rate on the left side panel and the accumulation on the right-hand side panel show that the polarimetric estimates, which are red and green line, are actually showing a moderate underestimation, whereas the blue line, which is the standard S to Z relation tuned for this region, shows really high underestimation of the amounts. Snowfall rates are like really low and not exceeding 2.1 millimeter per hour in for standard SOZ estimates, whereas SOKDPZ actually shows the most promising result and probably shows the best comparison with the ground measurement. But as you can see from this first part of the storm, when we have probably more aggregated snow, there is some underestimation, and then later there's some overestimation. I mean, overall, it's moderately underestimating the whole event. But if you remember from the beginning, the only tunable relation from this polarimetric relation is actually SOKDPZ. So this is just an example how we can actually switch from this predetermined or preset parameters for aspect ratio, which we use so far is 0.6, and the width of the canting angle distribution is around 15 degrees, which we found in literature. You have to set this a priori if you want to get any results. But with some tweaking and trying to match what we think was going on for this case, the aspect ratio and sigma are shown in these lower panels here. So by using these values, we can actually adjust SOKDPZ, and in this case, it matches almost perfectly with the ground measurement. And these are not what we have. We don't have the measurements for these, but it's more of an educated guess. But still, it shows the potential of these polarimetric relations, and of course, more research is needed to be done to find a way how to effectively estimate these two parameters and then use them in our approach. And to summarize, variability of SOZ relations is prohibitively large. So that gives the rise of these polarimetric relations approach of validity, and at least trying to do something about this in a manner that it's now available. So SOKDPZ relation is derived from Oklahoma snow to DVD dataset using a wide range of aspect ratios from 0.5 to 0.8 and width of the canting angle distribution sigma from 0 to 40 degrees. The SOKDPZ relations multiplier depend on the particle shape and orientation, but the change in density is partially accounted for because we use the proxy for the density in our 2DVD data. The relations exponents are almost invariant to the shape and orientation for SOKDPZ. SOKDPZDR is almost invariant to particle shape and orientation, even for size distribution variability, but it's vulnerable to error measurements, measurement errors of KDP and ZDR, and also ZDR miscalibration. So the aggressive spatial averaging is required to obtain more robust estimates of these polaritic variables, at least in S-band, and then we can use this more reliably as for KDP, Z, and ZDR. As we saw from this presentation, polarimetric relations for snow estimation are tested for several moderate or heavy snow events, and they show very good potential, for improvement in radar snow QPE. But further optimization testing of these algorithms is needed to mitigate the existing deficiencies. With this, I will conclude my talk, and thank you for your time, and any question is welcome.
Thanks a lot, Peter. Are there already questions from Slido? Somebody?
I had one.
Yes, please.
Please.
So thanks for showing all the challenges with snow retrieval. I guess there is also a challenge to get reliable reference on the ground. So what devices do you use, and how reliable are the actual values?
Well, so far, we actually have a really good addition to these ground validation tools. In the last 2 years, we acquired a Pluvio 400, which is a weighing gauge, so it's actually really accurate. But previously, we used a heated tipping bucket, and there was some underestimation, but that was all that we can do. And for some part of this 2DVD data set, we actually used just the regular buckets, and we had to wait for a day or two to melt and then estimate the amount that actually sublimated or evaporated, and then use that as a template or a ground validation tool for some of the cases at least. So our challenges are really big, wind driven, errors, then sublimation, a lot of other things that can, be taken into consideration. But this is really an experimental study, and it shows a really good potential. So basically, only the multiplier of this relation is affected because the exponents are not affected at all by changes in these parameters. So if there is a underestimation, it's probably affecting just the multiplier, and should be systematic bias, which should be fairly easily fixed if you have really good ground measurements.
Okay, thanks.
You talked a lot, that impressive talk on how to take all these variabilities in orientation and so on into account. On the other hand, it was also my understanding that there's also some kind of a decreasing information content of KDP towards the surface because of this increasing randomness of orientation and decrease in snowflake density and so on. Can you comment on that?
Yes. Well, that's why you have to use really aggressive azimuthal or spatial averaging, because if you can reduce the noise in KDP, then whatever is left there, even though if it's really small, it can give you, the sense that there is something there. And because these relations actually use Z and KDP, KDP is here as like a scaling factor for Z, basically. So maybe the caveat that I forgot to mention, if KDP is lower than 0.1 degree per kilometer, then it decreases the usability of these relations. So if you use RDQEP, then this is somewhat mitigated. I can tell you that the KDP in lowest, let's say 200 to 300 meters is not as good of a quality as in a little bit higher because of the way how KDP is calculated. Because you have to use about 6 kilometers in range in TDP to do this slope of the TDP and extract KDP. That translates to 200 to 300 meters closest to the ground. That, as you saw from these profiles, that it decreases the amount of precipitation which is estimated by SOKDPZ. SOKDPZDR is kind of similarly affected by this KDP reduction, but as I said, if you use some of these techniques and use extensive spatial averaging, it can be mitigated fairly successively, unless you have really high degree of aggregation, and then probably some adjustment needs to be made. Because what we saw so far, sometimes there is a bit of an underestimation, and there are a few cases that I looked into that there was a bit of an overestimation by using KDPZ relation. So it's a work in progress, but I can tell you that we're trying to find a way how to more reliably estimate these parameters as well. So far we use them fixed at some value 0.6, let's say, for aspect ratio, which is most common for aggregates. And sigma, we actually prescribe some linear profile from the dendritic growth layer towards the ground, which we found so far in the literature. But we are working on the estimates from radar of these parameters, and hopefully this will help with our goal to more reliably estimate the snowfall rate or accumulation from these relations.
Okay, thank you very much. I
Thank you
know
very
that
much.
there have been more questions in Slido, and the according people now entered the speaker room. Do they want to ask the questions directly, Jana or Raquel?
Yeah, I can do that. Can you hear me?
Yes.
Okay.
Yes.
If I understood that correct, at the base of your approach is to use a shape and an orientation factor.
It's for one of the these estimators that we developed for KDP
so
and Z.
for
These are
that,
affected.
yeah, for that specific one.
Yes.
So you showed these two plots, how you relate them. So, and for the shape factor, it's the aspect ratio that gets in. What is it for the orientation, actually?
It's a bit of the Canting angle distribution here.
Okay. And where do you get those from?
Well,
or do you estimate them on the run, or?
No, for now we're using just some estimates from the literature. So 0.6 is most common that we use for aggregated snow for aspect ratio, and for orientation we assign about 10 degrees in the dendritic growth layer and then linearly increase towards the ground, because in several studies there's been this increase in sigma with the degree, the higher degree of turbulence, or something like that. So we actually are working on the estimation of these on our own. There is a study from Matrosov that actually you can use even polarimetric radar to estimate the aspect ratio in dendritic growth layer or even lower. And for orientation factor, we are in the middle of development of radar-based approach that we can actually estimate this. That's all I can say for now, because I don't want to go too much further. We need to test a lot of these hypotheses and see if this is working. But so far, these middle grounds or some mean estimates are working fairly well. And if you did see this example that I showed, if you vary them, you can actually get really good results and really close to the ground estimate. So it's a work in progress.
Okay, thank you.
And this came from KDP, because KDP is prone to this variation in shape and orientation. Yeah, so, okay.
was another question by Raquel.
Yeah, can you hear me?
Yes.
Yes.
Okay. So my question was, why do you choose to compare using these cumulative plots instead of using some scatter plots where you can see if the snow rates fit for each time step?
No, that's a good question. But in this case, we wanted to show that the profiles should be close to like constant from the below the dendritic growth layer towards the ground. If the the hypothesis that the snowfall rate is mass flux should be constant below the dendritic growth layer, and as you can see from polarimetric relations, that fairly is accomplished. And S of Z does not show this type of profile. It's like going down towards the ground. So basically, what this shows, if you go higher up in the like radar elevation, then your Z will be fairly affected by this. But because KDP is much higher in the dendritic growth layer, you can actually use these values because they are much more reliable than close to the ground, and then forward them or project them towards the ground level. And of course, you need to take into account the snowfall velocity, maybe some dynamics winds. But this will give you probably some kind of a reference if you are estimating this really well close to the ground or not. So that was the reasoning behind showing these profiles. And these are experimental procedures yet, and these are novel approaches. We still are in development of these, and we are still trying to figure out what is the best way how to show the results and how to forward this towards the operational usage.
Okay,
yeah, thank you.
Does this?
Then thanks again, Peter, for this nice talk, and thanks to all of you for the inputs and discussions. But